Usually when we talk about heavy fleet operations, the expectation is that everything can be measured with just, like, mechanical certainty.
Right.
Like, a truck breaks down, a mechanic checks the engine block, they find a worn-out part, swap it, and the truck is back on the road making money. It's tangible, it's logical.
Yeah.
And mostly, it's predictable.
Well, I mean, that's the ideal world of classical mechanics, right? Very black and white, and everyone in logistics and mining really loves things that they can actually see and just put onto a routine maintenance schedule.
Yeah, exactly. But the reality on the ground lately is driving me, and probably a lot of you out there managing operations, completely crazy.
Mhm.
Our modern diesel engines are just facing this wave of mysterious failures.
Oh, yeah.
Maintenance costs are just blowing way past the budget, and these breakdowns happen out of nowhere. No warning lights on the dash. I mean, just last week, I had a 100-ton excavator completely die while climbing a 30-degree incline.
Wow. That's dangerous.
Very. No early symptoms, just boom, dead. It's an incredibly frustrating diagnostic nightmare.
And I can almost guarantee that when your mechanics tore that excavator down, they were probably super confused by the damage pattern.
Yeah, they were scratch threads.
Because the root cause crippling the industry right now isn't actually mechanical. It's happening at a microscopic chemical level. So welcome to this deep dive, custom tailored for you. Today we're putting your engines under the microscope, right inside the combustion chamber. We're going to break down this really crucial 15-slide technical presentation titled B35 B40 FAME versus renewable diesel, or HVO.
So our mission today is clear. We are hunting down this mysterious killer. You are going to learn exactly why your engine components are failing right now, and more importantly, how to mitigate this disaster until the real green energy solution arrives.
Let's get into it.
Yeah, so I'm looking at our source document right now, and right on the first page, there's this really striking visual. It's a split engine. On one side, there's a tube of FAME fuel, and it's this thick, viscous green liquid. And on the other side, a tube of HVO fuel that's clear blue, honestly, almost like mineral water.
Yeah.
And as an ops guy, seeing these side by side makes me a little skeptical. Does fuel color actually matter to my fleet, or is this just, visual marketing to sell a new product?
It's a fair question. A lot of people assume it's just industrial dye, but that visual difference on slide 1 isn't cosmetic at all. That thick green tube, that represents your current reality. That's B40, a fatty acid methyl ester blend. And, you can see that big red warning underneath about severe injector deposit risks.
Yeah, I see that.
Meanwhile, that clear blue tube is HVO, renewable diesel. And that clarity literally represents the absence of contaminants. This is a fundamental chemical divide that basically dictates whether your $100,000 diesel engine survives 10 years or, well, dies in 10 months.
This concludes slide 1. Let's move on to slide 2.
So let's look at the chemistry.
Okay, so if this clear HVO liquid is the holy grail, what exactly is hiding inside that green B40 liquid that makes it so toxic to my engines?
Slide 2 shows us the anatomy. Here's the 3D model of the FAME molecule. Notice the parts highlighted in red.
Yeah, the red sections.
So FAME, or palm biodiesel, is processed through transesterification mixing crude palm oil with methanol. But this leaves a massive fundamental issue that we call the oxygen factor.
The oxygen factor.
Exactly. FAME molecules carry a really high level of bound oxygen, and it's the presence of that oxygen in the molecular chain that makes it highly hygroscopic.
Hygroscopic, so meaning it actively pulls, like moisture right out of the air.
Not just pulls it, but locks it into the fuel structure itself. The molecule acts like a really aggressive chemical sponge for humidity.
Got it. So just to give an analogy for you listening, it's like leaving a dry biscuit sitting on a table in a humid room, right? In a few hours, it's just completely soggy from the air.
That's a great way to picture it.
But wait, I get that water in the tank is bad, but isn't the engine combustion chamber insanely hot? Wouldn't a little bit of moisture just, I don't know, evaporate and blow out the exhaust?
You'd think so, right? It's a logical assumption based on boiling water in a kitchen. But applying that to a modern diesel injector is fatal. The water doesn't evaporate peacefully. That bound water triggers the mechanical warning you see in the red box on this slide. It is the primary trigger for high-temperature injector failure. FAME literally invites water into a system that absolutely hates water.
This concludes slide 2. Let's move on to slide 3.
Now look at the contrast here.
Yeah, this is the DNA structure of HVO. It's a night and day difference.
What do you notice about the HVO molecular chain?
Well, it's just a long chain of pure hydrocarbons There's zero red highlighting anywhere, no oxygen at all.
Spot on. HVO is processed using hydrogenation. This high-level purification strips out every single oxygen molecule, resulting in a fuel that is chemically identical to pure fossil diesel. Because there's no oxygen, HVO is hydrophobic. It completely repels water, like a raincoat.
Wow. And looking at the matrix table on this slide, it says HVO is neutral as a solvent, and it's 100% drop-in fuel. I mean, just hearing that feels like a huge weight off my shoulders.
Oh, I bet.
So, zero blending limits. I could just fill up an excavator with pure HVO without changing a single hose or modifying anything.
You don't have to touch a single bolt. HVO erases all the operational anxiety that B40 brings. It's chemical perfection for an internal combustion engine.
This concludes slide 3. Let's move on to slide 4.
But as we know, B40 is what we're stuck with in the field right now.
Right. We got to face the music.
Exactly. So moving from invisible molecules to physical behavior, look at this split screen of the injector spray. On the left, you have this microscopic blue mist spreading perfectly. That's normal diesel atomization.
And on the right, with B40, man, it looks like thick green liquid dripping in these massive droplets.
That's the visual reality of density and viscosity. B40 is much thicker and denser than conventional diesel, and that viscosity totally ruins what we call atomization. Inside the chamber, you want the fuel sprayed as a microscopic mist so it mixes with air and burns instantly.
So we're basically forcing our high-precision injection systems to try and spray like a heavy syrup when they were designed to spray water.
Yeah, that's the perfect analogy. Syrup doesn't mist. It sprays in coarse, heavy droplets. And those big droplets have a terrible surface area to volume ratio, which means the combustion is slow, delayed, and just incredibly suboptimal.
That makes total sense. No wonder my drivers complain about sluggish throttle response and the engine feeling lazy.
Right.
The power isn't missing because the engine is broken, it's because the fuel is failing to explode fast enough.
Unfortunately, that power loss is just the start of the nightmare.
This concludes slide 4. Let's move on to slide 5.
Let's see what's happening inside the pipes. Here you see the green FAME liquid acting as a strong solvent.
Yeah, the slide shows the FAME aggressively stripping away this brown, dirty, crust-like legacy sludge from the walls of the storage tanks and the pipes. But honestly, as a fleet manager, seeing dirt get cleaned out of my pipes, my first instinct is, great, my engine's getting a free internal flush.
Careful. A lot of seasoned mechanics think the exact same thing.
Yeah.
But look at the directional arrows on that diagram. This isn't a gentle, friendly cleaning. FAME acts like a vicious chemical wire brush. The issue isn't that the pipe walls get clean. The issue is, where do all those years of dislodged sludge chunks go?
Ah, right. They don't just magically disappear. That heavy debris gets swept forward, riding the fuel pressure straight toward the engine.
Exactly. The document calls it a downstream threat. Massive amounts of residue that used to be safely stuck to the tank walls are now surging forward, creating an immediate threat of premature, massive clogging in your fuel filters.
This concludes slide 5. Let's move on to slide 6.
And if those filters get bypassed, that dirt slams right into the injectors. Speaking of injectors, let's go back to your question about water on slide 6. This covers HBCR, high-pressure common rail cavitation.
Okay, I'm looking at this pressure number, and it's terrifying. 2,500 bar.
It's extreme. Just for perspective, the pressure at the bottom of the deepest ocean on Earth, the Mariana Trench, is only about 1,000 bar.
Seriously?
Yes, your modern diesel engines are compressing liquid with 2.5 times the brutal force of the ocean floor.
That's insane. So how does the hygroscopic water from the B40 play into this?
This is where the thermodynamics go crazy. When the free water bound in the B40 is pulled into the injector chamber at 2,500 bar, it doesn't just get pushed out. It can't withstand that compression. The water actually changes phase, creates microscopic vacuum bubbles, and then implodes.
Implodes. So it doesn't blow outward like a firework. It collapses in on itself.
Precisely. That's cavitation.
And the visual here shows those microscopic implosions blowing these little craters into the steel surface of the injector.
The shock wave from a water implosion is unbelievably violent. It hammers against the hardest steel, gouging and blasting microscopic chunks of metal right off the surface. It pits the steel like the surface of the moon. And once those craters form, that free water instantly triggers rapid rust and corrosion.
This explains so much. I see injectors blown to pieces all the time, and I usually yell at my mechanics for not cleaning the tanks. But this water is literally acting like thousands of microscopic bombs destroying the hardest steel in the engine.
And it's not happening every now and then. It's happening thousands of times a minute while the engine is running.
This concludes slide 6. Let's move on to slide 7.
The damage isn't over. Slide 7 connects this cavitation back to the thick syrup issue from slide 4.
Okay, I see a combustion chamber diagram here.
Mm-hmm.
It shows that thick, unburned fuel turning into carbon into black soot.
The black soot you see coming out of the exhaust is just the tip of the iceberg. The document highlights the real danger: oil dilution. FAME has a very high boiling point. It refuses to evaporate, even in a hot combustion chamber. Because those coarse droplets don't burn completely, and they won't evaporate, the raw, unburned B40 liquid starts seeping down.
Wait, seeping down like past the piston rings and straight into the crankcase.
Worse than just getting in there. It reacts. This thick, raw fuel mixes with your engine oil, chemically degrades it, and forms a heavy sludge. It permanently destroys the oil's viscosity. The oil that's supposed to be super slick to prevent metal-on-metal friction just turns into sticky glue.
So for anyone listening, this is a massive operational red flag. It means checking the oil dipstick isn't just a routine top-off check anymore. If you smell fuel in the oil, or it looks thin, your engine block is basically on death row. Routine oil checks are literal survival checks now.
Absolutely. If the oil is compromised and you keep running it, your engine's crankshaft will grind itself to pieces.
This concludes slide 7. Let's move on to slide 8.
So if that's what happens while the engine is running, what happens when it shuts off?
Looking at slide 8, the injector tip here is completely deformed. It's covered in this black crust that the slide calls diamond hard, terminal coking.
Picture the moment a driver turns the key and shuts off the heavy machinery. The engine stops. But the heat inside that combustion chamber doesn't just vanish. That thick iron block radiates extreme resting heat, and right at that moment, you have residual B40 syrup clinging to the very tip of the injector nozzle.
Oh, man. Because the fuel flow stopped, there's no cool liquid coming through to cool down the tip.
Right.
So that leftover B40 literally just bakes alive right there.
That slow baking of residual fuel creates carbon coking. And this crust builds up asymmetrically in micron sizes, partially blocking the injector holes. So when they fire up the engine the next morning, this diamond hard crust deflects the spray direction. The precision geometry of the combustion is completely ruined. It sprays sideways.
Wow. Just last week, a driver reported a massive, sudden power loss right after starting the engine back up after a lunch break.
There you go.
It makes total sense now. The crust baked on while they were eating, and when they started it up, the fuel explosion wasn't pushing the piston straight down anymore.
Exactly. Direct consequence of asymmetrical combustion. You lose power and internal components vibrate way out of factory spec.
This concludes slide 8. Let's move on to slide 9.
So we talked about extreme heat baking the injectors. Slide 9 flips the script completely.
Yeah, now we're looking at cold temperatures. The visual shows the green fuel forming this thick white fog and sharp wax crystals. But the trigger temperature says less than 15 degrees Celsius. Wait, 15 degrees isn't even freezing.
Exactly. You don't need a blizzard to cripple your fleet. Remember, B40 is FAME. It comes from palm fats. And saturated palm fats have a pathetic tolerance for cold. When the ambient temp drops below 15 degrees, this fuel hits its cloud point.
Cloud point, where it turns cloudy and white.
Yes, and it transitions very quickly from that white fog into a critical phase called waxing. The liquid literally solidifies into sharp wax crystals and a thick solid gel. The palm fat is basically rebelling and trying to turn back into solid butter.
And considering 15 degrees is just like a chilly morning at high-altitude mines, this means B40 freezing is an everyday threat for us.
An everyday threat with fatal mechanical consequences. Let's look at the fuel filter visual on slide 10.
This concludes slide 9. Let's move on to slide 10.
See the filter here?
It is entirely buried, just entombed in a solid block of white wax gel. It says CFPP, cold filter plugging point.
The cold tolerance of B40 is tragically higher than fossil diesel. When those morning wax crystals get sucked up by the pump, where do they go? They slam right into the microscopic pores of the fuel filter. Because the wax is solid, within minutes, every inch of those pores is completely entombed. Fuel flow stops entirely. Period.
As a fleet guy, what you just said is pure horror. We call that sudden death from fuel starvation. I mean, picture that excavator I mentioned earlier, climbing a steep grade with tons of rock, and suddenly the fuel is choked off by wax. Engine stall.
Yep.
You lose hydraulic and braking power instantly. That's not just a repair bill. That's a massive safety hazard on a mining site.
It's a terrifying chain reaction, right? Starts with a microscopic cooling molecule and ends with a heavy machine dead on the edge of a cliff.
This concludes slide 10. Let's move on to slide 11.
Okay, the tension is high. Let's talk mitigation. Slide 11 moves from the problems to the mechanical solutions.
Finally, good news. I see a diagram of a high-spec water separator.
This is your first line of mechanical defense. Since B40 constantly inhales water from the air, you need water separators with daily drains. Your crew has to drain these every single morning, no exceptions. The goal is to physically drop that blue water out of the bottom before it ever reaches the high-pressure cavitation chamber.
Okay, I see the blue water at the bottom and the green B40 at the top. But what is this weird yellow layer sitting in the middle?
That is the most unexpected part of B40, biological sludge.
Oh, gross.
FAME is organic. When the water layer and the biodiesel layer meet, they create a perfect breeding ground for water-loving microbes and bacteria. They live in the water and feed on the organic carbon fuel above them.
So my fuel tanks are accidentally turning into bacterial aquariums?
Pretty much.
And the slide mandates biocide injection. So we literally have to play exterminator and poison these bacteria before they reproduce and vomit slime into our filters.
If you don't inject biocides, that bacteria will clog your system faster than any dirt.
This concludes slide 11. Let's move on to slide 12.
And speaking of filters, slide 12 shows a huge paradigm shift for maintenance.
The visual shows a pristine silver filter next to a legacy filter that is just completely crushed, black, and clogged from that solvent sludge we talked about on slide 5.
The message here is stark. The standard OEM maintenance intervals you're used to following, like changing filters every 10,000 kilometers or 250 hours, those are totally obsolete with B40.
It says here we have to cut filter replacement intervals by up to 50% under heavy loads. Man, cutting service schedules in half means doubling my parts budget. Is that really necessary?
Think about the alternative. If your filter gets totally clogged by B40's solvent, dirt, and wax gel, the pump pressure forces the filter into bypass mode.
Right, to keep the engine from starving.
Exactly. A valve opens so the engine doesn't die. But now the fuel rushing to your injectors is completely unfiltered. Sludge, sand, water, it all just free falls straight into your $100,000 engine block.
Okay, fair point. Buying twice as many filters is a lot cheaper than rebuilding an engine from scratch. This concludes slide 12. Let's move on to slide 13.
Beyond mechanical shields, slide 13 shows we need chemical warfare.
I see visuals of a red drop for detergent, a blue drop for demulsifier, and a yellow drop for CFI splashing into the fuel. Why aren't filters enough?
Because filters can't change chemistry. You need these three antidotes. First, the red detergent. It's specifically formulated to dissolve that diamond-hard carbon coating on the injectors when the engine is off, curing your terminal coating problem.
Nice.
Second, the yellow CFI, or cold flow improver. This actively breaks the bonds of the wax crystals, forcing the CFPP freeze point way down so your equipment doesn't stall on a cold morning.
And the blue liquid, the demulsifier. Does that tie back to the hygroscopic water?
Exactly. The water in B40 often doesn't separate on its own. It gets locked into a really tight emulsion. If the water is tightly bound, even the best mechanical separator can't catch it. The blue demulsifier forcibly breaks that chemical emulsion, freeing the water so gravity can pull it down to the bottom of the separator for you to drain.
So my takeaway as an ops guy, running B40 in heavy fleets without this specific 3-additive cocktail is basically corporate suicide.
Pretty much.
Without it, our mechanical defenses have massive holes. But assuming we have these defenses in place, we're safe to store the fuel, right? This concludes slide 13. Let's move on to slide 14.
Hold on, look at slide 14. Storage management. This is the final blow to old habits.
Oh, wow. It's a strict 3 months max shelf life. Why so short? A lot of fleets buy in massive bulk to lock in cheap prices and sit on it for months.
You're storing an organic liquid now, not a pile of coal. B40 has terrible oxidation stability. If it sits stagnant, the FAME reacts with oxygen and goes stale. The visual shows oxidized molecules forming long, sticky polymer chains. That's a deadly glue for your filters. Plus, look at the thermal insulation on the tank in the picture.
Why insulate a storage tank like a thermos?
Because drastic temperature swings like hot afternoons and cold nights cause the air inside a partially empty tank to condense. That condensation rains fresh water from the steel ceiling straight into your highly hygroscopic fuel. Thermal insulation stops the steel from swinging in temperature.
So managing B40 is more like storing fresh dairy in a high-tech fridge than storing conventional fossil fuel. This concludes slide 14. Let's move on to slide 15.
But let's take a breath, because slide 15 is the ultimate conclusion.
And the visual is beautiful. A pristine, glowing engine running that clear blue HVO from slide 3.
The document doesn't deny that FAME biodiesel is a vital green energy bridge mandated by regulations. We can't avoid it. But purely from an engineering standpoint, we've hit the absolute mechanical limit of what conventional engines can tolerate.
Right, and this slide states the true future for 100% reliability is pure HVO, or D100. The second we drop in this pure hydrocarbon, the water bomb cavitation, the diamond carbon coking, the freezing wax gel, the biological sludge, it all just vanishes instantly. Zero engine modifications needed. It's a completely drop-in solution with zero compromises.
Exactly.
For me, the biggest value of this final slide is hope. We aren't doomed to manage the pain of B40 forever. We just have to bridge the gap using separators, filters, and chemical additives until the era of pure, clean HVO energy finally arrives at our facilities. This concludes slide 15.
That's a brilliant operational summary. If we pull it all together, we see this incredible reality. Every single macroscopic issue that causes you stress, from a giant excavator dying on a cold mountain ledge to a cracked steel injector, every single one of them starts with a microscopic imbalance, the presence of one extra oxygen molecule in the fuel.
And for you listening, the folks actually running operations, this is exactly why we do these deep dives. When you're managing multi-million-dollar fleets, you can't just swap parts and cross your fingers.
Right.
Truly understanding why the steel shatters and how the chemistry reacts puts you firmly back in control. You're not just guessing in the dark anymore.
And honestly, this whole B40 versus HVO dynamic leaves me with one really provocative thought.
Well, let's hear it.
If we realize that just a tiny shift in chemical structure stripping oxygen from an ester to make a pure hydrocarbon can instantly cure the worst mechanical diseases in a hyper-complex engine, it really makes you wonder, what other impossible mechanical limits in our modern world are we just accepting as normal wear and tear when they're actually just waiting for the exact right chemical key?
Man, that is a puzzle that demands engineers and fleet operators to never stop questioning what we can't see. That is a heavy thought to close out our discussion. Thank you all for exploring these mechanical mysteries and chemical miracles with us today. Keep your fleets running strong, stay curious, and we'll catch you at our next deep dive.